In the previous lesson, we defined a taxonomy of the Italian railway infrastructure that has a dual role. On one side, it helps us to organize the railway components, establishing a uniform terminology. And on the other side, it provides a foundation for a proper energy modeling of this intricate energy system. In fact, a further push towards the decarbonization of this sector starts from a clear picture of the energy consumption in its current state. The taxonomy aims to aggregate all the different services related to the infrastructure into macro categories that may then serve as a basis for considering future alternatives. It allows the exploration of combination of different archetypes based on their nature, which can be used to analyze and foresee potential scenarios, such as the integration of renewable energy sources, the adoption of hydrogen and fuel cell technologies. In this context, archetypes represent distinct and representative patterns of energy demand at different levels of the taxonomy. Let's start by defining station archetypes. Station archetypes are found by evaluating parameters like available services, shops, and energy consumption patterns. The following table provides an example of 4 different stations that represent each of the 4 archetypes with their respective services and shops. These examples provide valuable insight into the station diversity and functionality within the network, allowing a deeper understanding of the different characteristics needed for the formulation of the energy demand for the given station. According to the defined taxonomy and the related archetypes, a station can be identified by a base load for the daily continuous consumption of electricity, such as lighting, heating, or cooling, followed by a variable load depending on the frequency of passengers and the probability of services use. In addition, stations can be characterized by the services that need to be provided to the train convoys, such as fueling stations and the dwell times in the facilities for origin-destination passenger trains. Following the taxonomy, line archetypes vary from the structural point of view, whether double or single rail, from the topological point of view, whether fundamental, nodal, or complementary, in addition to the operating power system, either electrified or depending on diesel traction. As seen in the table, the electrified lines archetypes can be differentiated by knowing the power system on the operator's line network. High-speed lines use special types of lines which are 25 kV double rail electrified, as opposed to normal electrified lines that operate at 3 kV. Modeling techniques can be used to analyze train schedules, passenger demand patterns, and energy consumption levels. By simulating different scenarios, such as adjusting train frequencies, optimizing routes, or implementing regenerative braking system, we can identify strategies that lead to reduced consumption and improved operational efficiency. As seen, vehicle classification sets the cornerstone for the types of vehicles according to the service on board, power, and passengers, while considering the routes. 4 types of trains characterize the Italian railway sector: regional, long distance, freight, and high speed. By taking samples from each, it will be possible to develop models for energy demand estimation and energy supply optimization. Modeling can support the design and development of energy-efficient trains by analyzing factors such as train weight, aerodynamics, and energy management system. By simulating different train configurations, propulsion systems, and energy storage options, we can identify optimal solutions that minimize energy consumption while maintaining performance standards. With reference to the table defining as an example regional train archetypes, it is essential to distinguish different energy consumption hotspots that occur both when the train is stationary, which are the services, and during its operation, a combination of power, weight, and maximum velocity. So for onboard services, the energy consumption can be quantified independently of the route and the number of passengers on board. Instead, it can only be determined by taking into account the travel time, since this is the main variables affecting energy consumption for services that operate continuously at maximum capacity. For propulsion, the energy consumption needs to be formulated by supplementing the information obtained from the definition of the line archetypes. This quantification will be based on the number of kilometers traveled, providing a comprehensive understanding of the energy requirements of train propulsion. The possible combination of archetypal stations, lines, and vehicles create around 97 archetypal routes. The identification of archetypal routes as functional units within an energy demand model is a significant outcome of this analysis, enabling the simulation and prediction of energy usage under diverse scenarios and the evaluation of decarbonization strategies. These routes act as representative samples of the entire rail service, allowing the accurate estimation of the sector energy consumption by providing a set of combination for the specific archetypes identified for station, vehicles, and lines. Incorporating these archetypal routes as functional units within the demand model enable us to simulate and predict energy consumption under different scenarios, taking into account the changes in service configuration, technology deployment, and other relevant factors, to assess the effectiveness of potential decarbonization strategies for specific routes, as well as for the system, ensuring that our proposed alternatives are not only sustainable but also economically viable. Analyze the rail service sector from an energy perspective, but in a comprehensive manner and with a robust and systematic approach that combines taxonomy, archetype definition, and demand modeling. Inform decision makers about targeted decarbonization measures and ultimately pave the way for a more sustainable and environmentally friendly future for railways, services, and transportation. More specifically, each archetypal route, given the methodology of formulation, represents a unique combination of services and infrastructure components that contribute to localized energy consumption patterns. By understanding these intricate relationships, the demand model can take advantage of the route as a functional unit, enabling granular and contextual analysis of energy demand hotspots and the drivers underlying them. These hotspots represent the primary targets for the implementation of effective decarbonization strategies.